This webcast discusses energy storage and energy pie charts. So, energy is somewhat difficult to define. We know that energy is the capacity for acting or being active. You know, when we say that someone has a lot of energy, we mean that they're able to do a lot. Energy is the capacity for doing work. And energy is a general cause of change. And we'll talk more about that in just a second. So, as we get to a definition of energy that is closer to what we mean in physics by energy, we want to understand that energy is a conserved, substance-like quantity with the capability to produce change in physical systems. When we say that it is conserved, we mean that there is a given amount of energy and it can move from system to system, but it cannot be destroyed and it can't be created. Substance-like means that energy can flow, it can move from one energy storage mode to another, from one system to another. And energy is a way that we measure the capability to produce change. If you look at a system and can detect a change in some of the attributes of that system, for example, position, how high is it off the ground, or changes in motion, is the speed increasing or decreasing, or the temperature, or the shape, is the spring compressed or is it stretched? When you see these changes, you can start to identify how the energy transferred between storage modes and or between systems. So, one thing that we need to discuss is that energy is energy is energy. It does not come in different forms. Now, in our common language, it is common for us to talk about, that's kinetic energy, that's potential energy, that's chemical energy or nuclear energy, and it makes it sound as if we're referring to different forms of energy. Really, though, when we talk about those things, we're talking about different ways of storing energy. So, for example, kinetic energy is energy that is evident because of the way an object is moving. Gravitational potential energy is energy that is evident due to the object's position, how high it is above the ground, things like that. So various modes exist where energy can be stored within a system, and these names that we use are really referring to those storage modes. Energy is always stored within a physical system. It has to belong to a physical object. It can flow or transfer from one storage mechanism to another within that system. So, for example, you imagine a ball that is held off the ground. It has some gravitational potential energy because of its height. If you release it, if you pull your fingers away from the ball, you'll see the ball begin to move faster as it moves down toward the ground. And so that gravitational potential energy is getting shifted or transferred into kinetic energy. So energy can flow from one method of being stored to another within the system. In this case, the system was the ball. Also, energy can transfer from one physical system to another. So if a ball is sitting at rest on the ground, right now it doesn't have a lot of internal energy, right? It's not moving, it's not above the ground or anything, but I could come along and I could kick that ball. So I would be transferring some of my energy, from my system into the system that is the ball. And so all of a sudden, after I kick it after I apply that force, now the ball will be moving. Perhaps it'll even be going up in the air. So not only is it moving, but it might be, increasing in height. So I have transferred energy to it. Always energy is conserved. So you should be able to see where it moves. It is never created or destroyed. Energy causes change as it transfers. Energy maintains its identity after it transfers. It is still energy, even if it is now stored in a different system or in a different storage mode. It is still the same type of energy. And our standard metric unit for measuring energy is the joule, Joule, which is abbreviated as an uppercase J. So we see change as energy transfers, and if more energy transfers, we should see more change. For example, I could stretch a rubber band just a little bit by applying a very small force on the rubber band. If I stretch it further, it takes a bigger force. I have to transfer more energy into the rubber band to see that I have stretched it even further. A music box. If I wind it just a couple of turns, it'll play a few notes before it stops. But if I wind it all the way up, then I'm going to get the entire song played. So as we transfer more energy into a system, we can get a bigger change out. There is an interesting analogy between energy and money. So for example, money is money is money. It can be stored in many different locations. I could have money in my wallet. I could have money in a safe under my bed. I could have money in different accounts at the bank or at an investment firm. In the same way, energy can be stored in different ways. Also, money can be exchanged between people and between accounts. I could shift money from my checking account to my savings account. Still my money, right? But it's just stored in different ways. So that's the same with energy. The ball that we talked about, holding it up in the air and then allowing it to drop. In that case, the total energy of the ball hasn't changed, but it has changed the way it's stored. Instead of being stored as gravitational potential energy by being high, it now becomes stored as motion, and we would call it kinetic energy. Also, money does not change form when it gets transferred. If I transfer money from my checking to my savings account, it's still money. If I take money out and put it in my wallet, it's still money. And the same thing with energy. As it moves from one storage mode to another, it's still the same thing. And money is conserved. There's a certain amount of money in circulation in the world, and energy is also conserved. So it can move around, but there's only so much of it. Energy is stored in a physical system as internal energy. And whenever the amount of energy in a system is changed, or even just redistributed between storage modes, some property of the system will change. And the properties that we're talking about would be, height, the elevation above the earth, speed, temperature, pressure, volume. So we'll look for these types of changes in the system as clues to how energy has redistributed within the system. In our class, we will mostly be talking about mechanical energy. And mechanical energy is energy that is due to something's position or its motion, possibly both. There are three major forms of mechanical energy. There's gravitational potential energy, elastic potential energy, and kinetic energy. And we'll talk about each one of them just a little. Right now, we're just trying to understand the types of energy and to be able to call them by the same by the proper name. And when I say types of energy, I really mean how energy is stored. Okay? So when we talk about gravitational potential energy, we're going to write that as E for energy with a G subscript. This refers to energy that is due to elevated position. So for example, that ball that's held above the ground, or water that's held in an elevated reservoir so you can let it run out, or a squirrel that has climbed up to a tall branch in a tree. Those things have gravitational potential energy because of their height above the ground. Our convention is that when something is sitting on the Earth's surface, it has zero gravitational potential energy. So something that's on the ground has no EG. And then the higher that something rises above the Earth, the more gravitational potential energy it has. Kinetic energy is written as E with a K subscript. Kinetic energy refers to energy that an object possesses due to its motion. Kinetic energy is zero when an object is not moving. And then as the speed increases, kinetic energy also increases. Elastic potential energy is energy that is stored in an object because it is undergoing a reversible deformation. And so here, we're using a spring to represent that elastic object. And when a spring is stretched or compressed, the material structure of the spring is storing energy elastically. The deformation of the spring, the fact that the end of it has been pulled or pushed one way or the other, is temporary. When the force that is stretching or compressing the spring is removed, the spring will return to its original position, and so it won't be deformed anymore. That's what we mean by reversible deformation. The spring can go back to its original shape. And while it is deformed, the spring is storing elastic potential energy. And now I want to talk just a moment about dissipated energy. This is really not a mechanical type of energy, but it's an energy that we need to be able to recognize. It's a storage mode for energy, but it's a dead-end storage mode. And when I say that, it's because we can tell where the energy has gone, but dissipated energy, it represents energy that is kinetic energy at a microscopic level, at the level of individual atoms and molecules. That energy, which causes those atoms and molecules to vibrate a little faster, it's unrecoverable, and it's not useful for other work. It can't be transferred then to another energy storage mode or to another system. Usually, energy is moved into the EDIS storage mode due to frictional forces, but it's also possible that it could be something like a loud noise or a bright light that gets generated. So even though energy is conserved, and see, this dissipated energy, we can see where it went. It's just that we're not able to then use it again. So even though energy is used, not all energy is equally useful. Okay, so just reviewing our, the storage mechanisms that we have mentioned. There is potential energy that's energy stored in a field between interacting particles. And the one that we will primarily be referring to is gravitational potential energy, which is called E with a G subscript. There's energy that's stored due to the reversible deformation of an object, and that's called elastic potential energy, which is E with an EL subscript. There's energy that's stored due to the motion of an object, and that's called kinetic energy, which is E with a K subscript. And finally, there's dissipated energy, which refers to random kinetic energy at the microscopic level as a result of friction, possibly sound or light. And remember, dissipated energy cannot be transferred into other energy storage modes. The other modes, gravitational, elastic potential, kinetic energy, can be moved in and out of those storage modes very easily. Okay, so we're going to start analyzing some systems to try to recognize, based on the changes we see in the systems, how is the energy redistributing between these storage modes. And one thing that we should understand is, remember we said energy is conserved. And if you have an isolated system, that's a system that has no interactions with other systems, then its energy will be constant. And so therefore the change in energy will be zero because its energy is constant. And that means that the internal energy of that isolated system is constant. The internal energy is going to equal the sum of the kinetic and gravitational potential energy, elastic potential energy, and the dissipated energy. If there's a change in one of the energy in one of those storage modes, for example, if kinetic energy decreases, then at least one of the other storage modes must show an increase in energy, right? Because the sum of all four of those things must stay constant if the system is isolated. We're going to use a tool called an energy pie chart to qualitatively analyze and show how energy changes internal to an isolated system. We will keep the circles, the pies, the same size to represent and demonstrate that the total energy of the system is constant. But the pieces of the pie will change size to show when energy that is stored in one mode or another is changing. Let's go and make a couple of these. So I'm going to go to our worksheet on energy pie charts. And so first I'm going to talk about using a rubber band. As a slingshot. Everyone has stretched a rubber band and made it fly across the room. And, when you first look at the rubber band, it's not taut at all. It's very relaxed. It's at equilibrium. And so there is no internal mechanical energy here. And so therefore we'll say that there's no pi of energy yet. But then when someone takes their finger and stretches the rubber band, now it is very taut. It has been deformed, and it's a reversible deformation, right? As soon as we take our fingers away, the rubber band's going to go back to being at equilibrium. But now there is a pi of energy, and all of that energy is elastic potential energy. It's all stored because of the deformation of the rubber band. And then if we're holding the rubber band taut, and if we release our fingers in the right way, all of a sudden we see the rubber band flying across the room. And I'm just going to make the assumption that there's no change in height. That's a simplifying assumption, but just bear with me because we're just starting to talk about these energy pie charts. So I still have the same amount of energy in this rubber band. I'm just talking about it as it's flying across the room, and it has not yet interacted with any other system. And so it did have a certain amount of energy stored as elastic potential energy. But as we watch it fly through the air, the rubber band is no longer taut. Right here it's very taut. But here it's a relaxed rubber band. Now what we see in this rubber band is that it's moving. And so all of that energy that originally was stored as elastic potential energy is now stored as kinetic energy. And that redistribution of energy from the elastic potential energy storage mode to the kinetic storage mode is evident in the changes we see in the rubber band. Let's look at a pop-up toy, and I have a very brief memo. Let me bring that up and play it. So when I talk about a pop-up toy, I mean, thought that I had that. Here we go. Okay, so here are little pop-up toys. You can get them on Amazon or whatever. And I'm just going to try to show the toy. Maybe I can't. Okay, here we go. So if you press the toy down, you're compressing the spring, and then it pops up and the toy flies up in the air. So let me just show that again. So the spring gets compressed, and then very quickly, the little toy just jumps up in the air. Okay, so we're going to consider a toy like that and demonstrate what's happening by showing how the energy is getting redistributed in the system that is this toy. Okay, so when we first look at it, we've got this little toy, and he is pressed down on the spring. So the spring is compressed. It's deformed. And so there's some energy in this toy, and it is all elastic potential energy. Now remember the types of energy that we're talking about. Gravitational. This toy at this moment has no gravitation. I'm going to draw it over here instead. So first we look at the toy, and it's sitting on a compressed spring. This is A. So it's on the ground. Then we're going to see it fly up and then fly back down. So then we're going to look at it, on its way up. Look, the spring is relaxed again, but it's moving up in the air. At the peak height, the velocity is 0 at the peak. Okay, so see how the height is changing, and also the velocity is changing, and the spring has changed. It was initially compressed, and then it relaxed. And then we're going to look at it one last time just before it hits the ground. So now it is moving down, and the spring is relaxed. Okay, so when we first see it, there is no gravitational potential energy. It's on the ground. There is no kinetic energy. It's not moving yet. But there is elastic potential energy. Then at position B, the spring is relaxed, so there is no more elastic potential energy. Instead, we now have some height, so there is some gravitational potential energy, and we have some kinetic energy because it is moving. At position C, we still have the same amount of energy. This is an isolated system. The toy is not interacting with any other systems. At the peak, there is no motion. Just for an instant, the velocity is 0. And so all of the energy at the peak is gravitational potential energy. And then finally, we're looking at it just before it hits the ground. It's moving really fast, okay? The height is essentially 0 because we're talking about just before it hits the ground. And so there, all of this energy is now stored as kinetic energy. So see how the labels on the pieces of the pie they change, and the sizes of the pieces of the pie have changed, and we can use these representations of how the energy is stored to explain the changes that we see in the system. Let's do one more of these. Let's talk about the wind-up robot walking across the table and coming to a stop. So, just a little guy, little robot, and he's got a spring inside. And as you have him, so first, he's fully wound up. He's not moving yet, but the spring inside this toy has wound up. So it is deformed with an elastic deformation. So right now the toy has elastic potential energy. Then in B, it starts walking across the table. The feet, slide against the table, and that means that there is friction. And that's important because when we have friction, we have to overcome it. The friction causes the feet and the table, they both heat up a little bit. They get the molecules and atoms on the feet and on the table, they get just a little bit faster. They're excited by the friction. That's microscopic kinetic energy, but it is not recoverable. So there is some dissipation because there is some friction. The toy is moving, so there is kinetic energy, and the spring, it is unwound a little bit, but it's still, it has not returned to its original shape. So these are two springs in problem 2 and problem 3. In problem 2, the pop-up toy, that little spring almost immediately pops back to its original shape. But in something like a wind-up robot, the spring takes a little bit of time to unwind and return to its original shape. And so we have less elastic potential energy than we did in A, but there is still some. Otherwise, the robot wouldn't move anymore. And then at the end, it has stopped. So it still has the same amount of energy, but none of the energy is elastic potential energy anymore, right? The spring has returned to its original shape. It's not moving, so there is no kinetic energy. So at this point, all of the energy has been dissipated. Let's look at number 4. So the ones that we've looked at so far, they all started with elastic potential energy, and I want to show you that everything doesn't have to start with that. Let's talk about just a ball, and you give it a little shove and it starts moving. So we're looking at it after it was given the push. Okay, so we're just looking at the ball as our system, and right now it is moving. And so it has kinetic energy. By the way, you never show dissipated energy in the first view. So this ball is rolling, sliding across the table, but when we first look at it, it has just started moving. It has not covered any distance, and so we're not going to show any dissipation at that point. Okay, but at position B, it's still moving, but it is slowing down. The reason it's slowing down is because it is overcoming friction. Friction is opposing its motion, and so some of this energy is being dissipated due to the friction. It's going into exciting the little molecules and atoms on the surface, and those microscopic kinetic energy that we can't get back. So it's dissipating some energy, but it's still moving, so there's kinetic energy. There's less kinetic energy because the speed is slower. Okay, and then finally it stops. So there's no more kinetic energy. All of the energy that was given to it by that shove has now been dissipated. Okay?